All right, today we're going to look at the review over Chapter 8, Topics 5 through 11. The first few are just rewriting into exponential form, pretty straightforward, the relationship between logs and exponents. So for number 1 here, we have 2 to the 4th is equal to 16. That would be exponential form. Number 2, 1/2 to the negative 1 equals 2. Number 3, 81 to the 1/2 equals 9. Remember, the 1/2 means square root. The negative exponent means to flip it. Number 4, we have common log of 100 equals 2. So remember, no base written here, it's a base 10. So 10 to the second power equals 100. Natural log of 3 equals x. So natural log has a base of e, so e to the x equals 3. And once again, common log has a base of 10. So 10 to the negative 1 equals 1 over 10. The next few we were going to write in log form since they start in exponent form, so just the opposite. So for number 7 we have log base 36 of 6 equals 1/2. Number 8 we have common log of 1 over 100 equals negative 2. Number 9 we have log base 9 of 27 equals 3/2. Number 10, we have common log of 1,000 equals 3. And you can put these things in parentheses if you want inside the log. It's not a big deal. 11, natural log of x equals 3. 12, natural log of 4 equals x. For the next few, we were trying to evaluate. Technically, you can put these in the calculator using the change of base formula, but most of these should have been pretty simple to evaluate without doing that. So log base 5 of 125. 5 to what power is 125? That would be 5 to the third power. Log base 3 of 1 over 81. Well, 81 is a power of 3, but it's in the denominator, so it's going to be negative. And it's a fourth power is 3. 3 to the negative fourth power is 1 over 81. Log base 8 of 4, so 8 to what power is 4? Now, this one, if you're uncertain, you may have to set up an equation to do these. And some of these, I'm not going to do it for all of these, but you can definitely set up an equation to do these. Or, of course, you can put them in a calculator. But let me just do one of them so we can see how the equation works. So remember, the way that you do this is you set it equal to x. But I mean, you could just put this in the calculator, honestly. You could put this in as common log of 4 over common log of 8. And it'll tell you the answer. But I'm going to do it the way we used to do it. So then you can set this up as an exponential equation. 8 to the x is equal to 4. You can make the bases the same. So this is 2 cubed. And this is 2 squared. So you got 2 to the 3x equals 2 to the second power. Then you set the exponents equal to each other. 3x is equal to 2. Divide by 3, x is equal to 2/3. The benefit of doing it this way is because when you put it in the calculator using the change of base formula, common log of 4 over common log of 8, it's going to give you a decimal. It's not going to give you the fraction like 2/3. Unless you hit the fraction button, then maybe it will give you the fraction. But you could just put this in the calculator if you wanted to. But this is the way we used to do it. But anyways, it is going to be 2/3. Okay, and the reason for that is because to get 4 from a power of 8, you would first have to take the cubed root, so that's the 3 in the denominator, and then you'd have to square it, because the cubed root of 8 is 2, and 2 squared is 4. So 1 over 25, log 1 over 25 of 5, so the square root, so it's going to be a fraction, 1/2, and it's flipping it, so it's going to be negative, so negative 1/2. Common log of 1 over 100, so it's in the denominator, so I would need 10 squared, but a negative, so negative 2. Natural log of e to the fourth, so this is asking e to what power is e to the fourth, and of course, e to the fourth power is e to the fourth. Natural log of 1, any log of 1 is just 0. And common log of 10 of 0.1, so that's actually negative 1, because that's 1 over 10, so negative 1. For our log equations here, we need to solve them, so that can require a couple of different things. Number 1, log base 5 of x equals 25, so we would switch this to exponent form. 5 to the second power equals x. So we see that x is equal to 25. Number 22, log base 36 of x equals a half. So we switch this to exponent form. 36 to the 1/2 is equal to x, and 36 to the 1/2 power is 6. Number 23, I mean, there's no reason to switch this because log base 2 of 8 is something you can do. Log base 2 of 8 is just 3. So we're looking at 2x plus 1 equals 3. Subtract 1, 2x equals 2, divide by 2, x equals 1. So that one, not too hard. So number 24, we have log base 2 of 2x plus 4 equals 1. So first we change this to log form, or exponent form. So 2 to the first power equals 2x plus 4. So 2 equals 2x plus 4, and then we solve it. Subtract 4, negative 2 equals 2x, divide by 2, x equals negative 1. Number 25, log base 3 of x minus 4 equals 2. Okay, so we change this to exponent form. So 3 to the second power equals x minus 4. So 9 equals x minus 4. Add 4 on both sides, x equals 13. Number 26, log base 3 of 4x equals log base 3 of x plus 3. Okay, so this is a log problem where we have logs on both sides. So this is the easy problems. We can essentially ignore the logs. 4x is equal to x plus 3. Because in order for these to be equivalent, the logs are already equivalent. The insides of the logs need to be equivalent. So we can just solve this equation. Subtract x, 3x equals 3. Divide by 3, x equals 1. Number 27. Log base 4 of x plus log base 4 of x minus 6 equals 2. Okay, so this is the properties of logs. We have two logs on the same side added together. So in order to put these into a single logarithm, we have to multiply what's inside of the logs, x and x minus 6. So if you multiply x times x minus 6, you get x squared minus 6x. Next, we need to change this. Once these are combined into a single log, we have to change this to exponent form. So we get 4 to the second power equals x squared minus 6x. Okay, so that's 16 equals x squared minus 6x. This is a quadratic because of the x squared. So in order to solve a quadratic, we have to set it equal to 0. So x squared minus 6x minus 16 equals 0. And then we need to factor this. X squared minus 6x minus 16. This factors into x minus 8 and x plus 2. So we got two solutions here. We got two zeros, x equals 8 and x equals negative 2. Now if we check these back in the original problem, 8 is fine because you plug in 8 here, log of 8, and you plug in 8 here, log of 2. That's fine. But negative 2 does not work because if you plug it in here, you take the log of a negative number, which is not acceptable. Can't take a log of a negative. So this one does not work. X equals 8 is our only solution. So 27, x equals 8. 28, 2 times log base 5 of x equals log base 5 of 25. There's a couple of ways to do this one. One of the ways would be to put this 2 back inside the exponent, back inside the logarithm using the power property and making it the exponent, giving us log base 5 of x squared equals log base 5 of 25. And now since we have logs on the same side, we know that x squared would have to be equal to 25. Square root both sides, don't forget plus or minus, and we get x is equal to plus positive 5 and x is equal to negative 5. Now the negative answer does not work here because when you plug it in, you take the log of negative 5, which you can't do. So the only answer that works here is 5. '29, we have log base 3 of 40x minus log base 3 of 5 equals log base 3 of 24. All right, we have to use the properties of logs to combine the ones on the left side into a single logarithm. So since the 5 is subtracted here, it's not going to be multiplied in the numerator, it's going to be divided in the denominator when we combine it. So we get log base 3 of 40x over 5 equals log base 3 of 24. 40x over 5 is just 8x. So we get log base 3 of 8x equals log base 3 of 24. Logs on both sides, so we don't have to change the form. We can just set the insides equal to each other. 8x equals 24. Divide by x, or sorry, 8, x is equal to 3. 29, x is equal to 3. Number 30, we have common log of 3x plus common log of 2 equals 1. Okay, so once again, we have to use our properties to combine these into a single log. So that gives us the common log of 6x is equal to 1. Now since there's log only on one side, we have to change the form. And remember, the base here is 10 because it's a common log. So 10 to the first power equals 6x. Okay, so 10 equals 6x. Divide by 6. X equals 10 over 6, which can be simplified to 5 over 3. Number 31, 3 times the natural log of 2x is equal to 15. Now, we could technically use the power property, put this exponent of 3 back inside the logarithm. However, since it's multiplied and we can get this natural log by itself, the easy thing to do is just divide by the 3. We couldn't do that in the other problem because both sides had a logarithm, but this one, only the left side has a logarithm. So we're allowed to divide the right side by 3 without a problem. And we get natural log of 2x equals 5. Switching this to the exponent form, we get e, because that's the base of the log, to the 5th power equals 2x. Solving this for x by dividing by 2, we get e to the 5th power divided by 2 is equal to x. And this is something we can easily put in the calculator, e to the 5th divided by 2, which is about 74.2066. Number 32, we have the natural log of x minus 2 equals 3. So we'll put this in exponent form. So e cubed is equal to x minus 2. We'll solve for x by adding 2. So e cubed plus 2 equals x. And then we'll just put that into the calculator, e cubed plus 2, which is about 22.0855. All right, now the next ones were exponential equations that we were solving. So number 33, we have 5 to the x power equals 20. So we'll change this to log form. So log base 5 of 20 equals x, and then we can put this in the calculator by using the common log change of base formula, common log of 20 over common log of 5. So common log of 20 divided by common log of 5, and we get our solution is about 1.8614. Yeah, 1.8614. Okay, number 34. We have 2 to the x minus 1 plus 3 equals 12. So before we can change the form here, we do need to get the exponential part by itself. So we'll subtract 3 to do that, and that gives us 2 to the x minus 1 equals 9. Now we can change it to log form. So log base 2 of 9 equals x minus 1. We can solve this for x by adding 1. Log base 2 of 9 plus 1 equals x, and then I can calculate this using the change of base formula. So the common log of 9 over the common log of 2 plus 1. So common log of 9 divided by common log of 2 plus 1 is about 4.1699. Number 35, 9 to the 2x is equal to 4. Can change this to log form, so we got log base 9 of 4 equals 2x, and then we can solve for x by dividing by 2. So we got x is equal to log base 9 of 4 over 2. We can convert this to common log so that we can put it in the calculator. So common log of 4 over common log of 9, and then divide that by 2. So common log of 4 divided by common log of 9. Divide that by 2. It's about 0.3155. Number 36, 10 to the x plus 1 equals 4. So log form, we have the common log of 4 equals x plus 1. Subtract 1. We got the common log of 4 minus 1 equals x. And we don't need to use the change of base here because it's a common log, so we'll just take the common log of 4 and then subtract 1, get negative 0.3980. 37, we got e to the x minus 4 equals 7. So we need to get the exponential part by itself, so we'll get that part by itself by adding 4, so 7 plus 4 is 11. Then we'll change this to natural log form, so the natural log of 11 equals x, and that we can easily put in the calculator. Natural log of 11 is about 2.3979. And then number 28, we got 2 times e to the negative x plus 5 equals 19. So first we need to get that exponential part by itself. So that's going to be subtracting 5 first. So 2 times e to the negative x equals 14. But then we also got to divide that 2 out to get rid of that. So we get e to the negative x equals 7. Now we can change this to log form. So the natural log of 7 is equal, whoops, it's getting messy here. Natural log of 7 is equal to negative x, and we don't want a negative x, so we'll divide by negative 1. So we want the negative natural log of 7, and that will give me the solution here that I'm looking for. So negative natural log of 7, or the natural log of 7 divided by negative 1 is fine too. It's about negative 1.9460. Numbers 39 and 40, we were using the compounded continuously formula, a equals p times e to the RT. Number 39, initial investment of $1,000, so principal is $1,000. The rate is 6.2%, which as a decimal, that's 0.062. The time period is 15 years, so this will just be a matter of plugging into the formula. A is equal to 1,000 times e to the 0.062 times 15. So e 0.062 times 15 power multiplied by 1,000, and we get our final amount, $2,534.51. Number 40, a savings account is set up with an initial balance, so P equals 25,000. The rate, 9%, so 0.09. How long will the money need to stay in the account to double in value? Okay, so the final amount needs to be double 50,000. Okay, so we're actually not solving for, we're not just plugging into the calculator. We have 50,000 equals 25,000 multiplied by e to the 0.09t. All right, so we need to solve this exponential. The first thing we'll do is divide. We need to get the exponent part by itself, so we'll divide by 25,000. Whoops, that's not, can't just cross that out. What am I doing? 50,000 divided by 25,000 is 2. So 2 is equal to e to the 0.09t. Switch this to natural log form, so the natural log of 2 is equal to 0.09 times t. Divide by 0.09. So the time period can be calculated by doing the natural log of 2 and dividing by 0.09. So natural log of 2 divided by 0.09. So about 7.7 years. So almost 8 years for it to double in value there for number 40. And the last example, number 41, we want to graph the log function log base 2 of x minus 1 plus 2. Okay, so this is a transformation of log base 2. It is shifted to the right 1. We will have a vertical asymptote at x equals 1, because that would make the inside of this 0. So it is going to be to the right of this here. The first number I'll plug in then is 2, because if I plug in 2, I get log base 2 of 1 plus 2, so 0 plus 2. So plugging in 2 gives me 2, so my first point that I'm going to apply is right there. The next number I want to plug in should give me an output of 3, hopefully, which means I would need 4 inside this parentheses here. Well, no, I would need 2, because I want this to be 1 plus 2. So I want to plug in 3 then, because log base 2 of 3 minus 1 plus 2, log base 2 of 2 plus 2, so 1 plus 2. So I want to plug in 3 in order to get 3. So my next point is 3, 3. And then the next number that I want inside the parentheses is 4, because I want 4 out of this function. And the next number I want inside the parentheses should be 4, because 2 to the second power would make 4. So that's going to have to be 5, because then I would do log base 2 of 5 minus 1, which is 4, and I get 2 plus 2, which is 4. So 5, 4, and I think this is enough. Three points is plenty. All right, so my domain is from 1 to infinity, because the asymptote to infinity. The range is all real numbers. Now the x-intercept, this one we didn't really talk about that much, but remember the x-intercept is where the function output is 0. So we would say 0 is equal to log base 2 of x minus 1 plus 2. And we can solve this equation. We can definitely solve this equation. We can add 2 to both sides, giving us 2 is equal to log base 2 of x minus 1. And then we can switch this to exponent form, which is 2 to the second. Oh, sorry. I was supposed to subtract 2 here. Sorry, let me fix that. So minus 2 on both sides. So 0 minus 2. So that's negative 2. Switching this to exponent form, I got 2 to the negative 2 is equal to x minus 1. Add 1 to both sides. So my x value of my x-intercept, which is where the y coordinate is 0, is 2 to the negative 2 plus 1. Okay, so that's 1 over 4 plus 1, so like 1.25. Now, even though we didn't look at this, we do have all the tools to do this, and we just had to remember that plugging in 0 for y is how we get the x-intercept. The y-intercept, on the other hand, would be plugging in 0 for x, but you can't plug in 0 for x. There's no y-intercept here. It doesn't even cross the y-axis, so none. All right, and that is the entire review.